community. OpenMined is an open source community focused on researching, developing, and promoting tools for secure, privacy-preserving, value-aligned artificial intelligence. Our goal is to build safe artificial intelligence for everyone. In this AMA interview, you'll have the opportunity to ask questions of privacy experts from in and around the OpenMined community. My name is Amel Salani, ladies and gentlemen. I'm from Sfax, Tunisia, and I'm an AI engineer working at a company named Unsteady, and I'll be your host for the day. Today we're having a very special guest from Ruppert Labs, Morten Dahl. Morten holds an MS in Theoretical Computer Science and a PhD in cryptography. He currently works as a research scientist at Ruppert Labs, a startup focused on taking privacy-preserving machine learning to production. Previously, he led the cryptography team at Snips, a startup focused on building private by design machine learning systems for mobile devices. He is a member of OpenMined. His work has primarily been on encrypted deep learning and secure federated learning. This includes TF Encrypted, an open source project for encrypted deep learning in TensorFlow, an SDA and SDA, an open source project for secure federated learning on sporadic devices. Welcome, Morten.
Great. Thank you for having me.
Great. Thank you for being here today with us. So, Morten, we had like more than 25 questions submitted beforehand for you to answer. And in the next 30 minutes or so, we're going to try to answer as many as possible. Are you ready?
Sounds good. Yeah, let's do it.
Okay, great. So the first question is like, what is the difference between differential privacy and federated learning?
So it's two different techniques of kind of dealing with issues that arise around privacy. So federated learning is the idea of saying the data stays with the data owner, but we can still train on it. So instead of sending the data to whoever wants to train on the data, we're sending what we want to train the model to the people that have the data. And then we do the training locally on their devices. And we bring only back the model, the trained model afterwards. And then we can do this in an iterative process where we're never moving the data. We're just moving the model around the old model and then the updated model. And then we iterate on this. Differential privacy, on the other hand, is essentially a tool for the safe release of data. So it means that if you have a data set that you want to release to the public, but you're worried about this data set containing too much personal information in it, you can essentially add a bit of noise to this data set in such a way that when it's released, you can give some mathematical guarantees that everyone inside the data set has some plausible deniability around whatever is leaked about them. So in other words, if you can guarantee that no one can pinpoint your age, for instance, within a certain interval, even if they can do whatever they want with this data afterwards. So it's two techniques which are often combined. So you would say, for instance, in the federated learning process, you might say that as part of you're never seeing the training data directly during the training process, but the model that you get afterwards might have learned too much about the training data itself. So even if the training data itself was never seen, was never moved away from whoever originally had the training data, the model you get afterwards might actually have learned too much of this training data and can now expose sensitive information about the individuals that were in the training data. But then you can add differential privacy as part of this process, which essentially says that the model afterwards, or ensures that the model afterwards is not leaking too much about the training data either. So the two things work great in combination, but they're solving slightly different problems.
Great, cool. So another question is, what is the difference between federated learning and secure multiparty computation?
So federated learning is not, all the privacy guarantees you get from federated learning is from the fact that the data stays with the data owner and you're only sending the model around. Secure computation, on the other hand, is a technique for taking any kind of computation and then doing it on encrypted data instead. So it means that you could, in principle, federated learning, where you're training the model by sending it to the data owners, then generating an update, and then iterating this process. In secure computation, you could imagine sending the training data in encrypted form into a training process, and then performing the training on the encrypted data, and arriving at a model that way instead. They're also sometimes used in combination as well. So for instance, in federated learning, you often see this thing called secure aggregation. And that means that When you have different parties with data in a federated learning setting, they're all generating an update to the model. Now you want to take this model update from all the different data owners, and you want to aggregate it in some way. You can do this in the plain text, but as we talked about before, there might be some leakage coming out of the training data through this means. So what people have proposed in addition to differential privacy is to also aggregate in the encrypted space. So what that means is that instead of sending the plain text gradient updates back to the model owner, you are sending it into an encrypting process using MPC, where all the individual gradients are encrypted, then aggregated while they remain encrypted, and then only the aggregated gradient is released to the model owner. In this way, you're achieving the same result, but if you're doing so in combination with, for instance, differential privacy, you often end up adding much less noise to the gradient that you end up with, if that makes sense.
Yeah.
So federated learning can be used for different models and different techniques as well. But secure computation is a larger concept, so it can be used for other kind of machine learning processes as well, even for other kind of computations as well. So it can be used for electronic markets, including auctions. It can be used for various things in finance, in terms of matching up data sets and so on. And it's not just limited to the training scenario.
Nice, great, cool. So third question is, what is the difference between homomorphic encryption, secure MPC, and secure hardware?
Great question. So this is different techniques for doing secure computation. So this is a field that goes back to the 80s, and many different approaches to how do we compute on encrypted data has evolved over the years. And the first one that came out was actually called garbled circuits. I'm not planning on going into the technical details of how these works, but they are essentially solving the same problem, but just in different ways. So garbled circuits is one approach. Homomorphic encryption is another approach. Secret sharing is a third approach. The thing is, all of these are based on mathematics. So all of these are software-based solutions in the end, where the security guarantee is, of course, from the correct implementation of the software, but then also otherwise only from the mathematical proofs that these are actually secure. Secure hardware, on the other hand, is again also a question of, is implementation secure? But the security guarantee there lies with the hardware manufacturer. So in other words, you get to choose between, do you want to trust the hardware or do you want to trust the mathematics behind it, in addition to whether or not the implementation is correct. But essentially, they all implement the same basic functionality, which is how do we compute on encrypted data, or data that somehow remains in a scrambled form. The difference between them at a more technical level is what kind of performance can we get? What kind of models are they suited for? What are the trust assumptions we want to make around how many parties are involved in the computation? How large models are we dealing with, and so on and so on. And picking, so for instance, if you're training a neural network, picking the right technology is also critical for actually getting good performance.
Yeah, I suppose. Yeah, great. Okay, thank you for the answer. Another question is, how much time is lost when doing a privacy-preserving machine learning training, comparing to a training with the same model, dataset, and hardware, but without privacy preserving?
That's a great question. So again, it depends on what we specifically mean with privacy preserving machine learning in this case. If we talk about federated learning, then of course there's various questions around, now these data sets are disjoint as opposed to in one large place. How does that affect the machine learning process itself? Does it slow down? Does it mean you have to have more iterations to get the same accuracy and so on? There's also the question of networking back and forth. So now you're sending the model around. If it's a very large model, that can be quite expensive and so on. If we're talking about differential privacy, then we have some of the same problems around when we're adding noise to the data. Does that mean that we have to use more iterations? Do we need to be more aggressive on our training process and so on? So there can also be a slowdown there. If we're talking about secure computation, then there's definitely a slowdown there because we're now no longer computing on plain text data, right? We're computing on encrypted data, and there is a significant overhead in this. I think for MPC, for secure computation-based techniques, it's currently between 1 or 2 orders of magnitude that this will slow you down on, for instance, on a neural network. There are some limitations in this around the amount of networking So in some of the techniques, you have to send a lot of traffic between various players in the secure computation, and that has an overhead. In some of them, for instance, in homomorphic encryption, there's a large computational overhead where the computations we're now doing is no longer on, let's say, 64 bits, but maybe on 1,000 bits or 2,000 bit numbers. So that's obviously slower to compute on. If we're talking about enclaves, which to some extent are running using the same hardware as you would do in plain text, the problem there is that there are memory limitations inside the enclave, so you can't have too much data in there. If the model gets too big, if the values throwing through the network are too large, then you have to swap out and use the memory of the host system. There's an overhead in this and so on. So I think it really depends on what kind of technology you're talking about particularly. Although I do think sometimes the more relevant question is, what is the extra cost of doing this? Because when I said before that things like MPC is maybe 1 or 2 orders of magnitude slower, that's not always an entirely fair comparison, because you could run that number. It might be between a plain text, a CPU computation on plain text versus, let's say, 2 very powerful machines running the secure computation. So the cost of running this, for instance, on GCP or AWS is going to be significantly higher in the secure computation setting as compared to the plain text setting where you're running on a single CPU. So in the end, that boils down to, is the use case you're having, can that compensate for the extra cost of running the computation? And that cost can be compensated by, well, I guess the easy one is that if you can't even do this computation in plain text, so if there's no way you can get access to the training data, for instance, if it's in plain text, then if there's a high cost, but you can do it, then maybe that's worth it. It can also be that you can get access to the data, but only in a way where you have to involve a third party that's willing to can guarantee through legal contracts and so on that this data is never leaked. And then it's the question of what is the fees that this guy would normally charge for offering this service, and can then that be compensated by the cost of actually running the secure computation. So in other words, it depends on the technology, and maybe cost is more relevant. And comparing that to what is actually the benefits of being able to do this on the encrypted space.
Yeah, totally agree. Thank you. So another question is, what level of the prerequisite knowledge of math you would recommend to someone who's getting into the field of private ML?
So that's a good question as well. It's again, it depends a bit on the technology we're talking about. So if you're talking about differential privacy and federated learning, federated learning is mostly, in my experience, requires knowledge in machine learning. So that's a question of how do you adapt models to train on disjoint data sets that are not necessarily coming from the same distribution? What is a good aggregation strategy, and so on and so on. If you're talking about differential privacy, then it's more a question of statistics, analyzing these kind of mechanisms for figuring out if they're actually, how much differential privacy they can guarantee. If we're talking about secure computation, so moving into the encryption space, then again, it's slightly different. There it will be, I think a good place to start would be to have a solid understanding of algebra. So my background was in computer science. So when I started graduate studies on cryptography, I was definitely spending a lot of time reading up on abstract algebra, which all of a sudden had a concrete application. So that was nice as well.
Yeah, exactly. Great. So another question is, where are good grad schools for privacy preserving AI? Do you have any recommendations?
There are a few research centers around. I don't know if we keep a list somewhere. I know we do have a few awesome lists where we try to gather some of these resources. If we haven't put the graduate schools on there yet, then we probably should. At least for privacy preserving ML and for secure computation and so on. For the latter, there's definitely a few good universities around. So there's a few in the US. University of New York University comes to mind, Columbia, MIT, Berkeley, Stanford, kind of the usual ones, I suppose. In Europe, there's one in Denmark, which is really good. There's one in Israel by LAN, which is very good. There's one in Leuven, which has a big research group as well, working on secure computation. I'm sure I'm missing a few. I think the best approach would be to go either to, so Archive is good for the more machine learning oriented privacy preserving ML, so differential privacy, federated learning. But if someone is interested in crypto, the best place to go is actually to the ePrint. So there's ePrint, International Association of Cryptographical Research, where all the papers are published. Same principle, just a different catalog. And then simply go through the papers there, the more recent papers that get mentioned, and see who are the people behind it, gather some statistics about what are the most popular published researchers, where do they come from, and so on.
Yeah, thank you. Great. So, what are good research topics for people interested in doing research in ML and cryptography?
So, I do think privacy preserving machine learning is really the intersection of different areas. As we already talked about, there's the machine learning aspects, there's the crypto aspects. There's also a data science aspect to it, where we really need to find, as we briefly talked about before, we need to find the right applications for this stuff, because there is a price attached to it. There is an overhead in doing things in the privacy space, but there's also an opportunity of finding new use cases. And actually finding those use cases, I think, comes from industry, comes from people that want to do very concrete things. And maybe we can label those as being the data scientists. So they have the everyday problems. They're curious about solving problems that really matter to them and in their context. And now they want to apply these technologies. So that's one approach. Simply saying, I don't need to understand all the machine learning, I don't need to understand all the crypto, but I want to start figuring out where can privacy play a part in my context, in terms of opening new opportunities or reducing the overhead of doing this with plain text data. And then, of course, there's machine learning researchers that want to adapt models, that need to figure out, essentially, you can see secure computation, for instance, as a new kind of computational device. And with every new type of computational device, we need to adapt machine learning models to kind of take advantage of that. And then, of course, there's also cryptographers that are now taking the techniques that were before. As I said, when we started, secure computation has been around since the 80s, and many of the frameworks that's been developed so far has been targeted more towards the kind of general purpose computation and less towards machine learning. And we need cryptographers as well that's interested in adapting some of the existing techniques to really fit with the machine learning use cases, operations we need there in order to get better performance. And then finally, there's also a huge engineering effort involved in this. One is to implement some of the crypto and doing that efficiently to reduce this extra overhead that we're talking about. Another one is to say, how do we actually express these computations, which are now sometimes distributed? For instance, if we're talking SQL sharing and MPC, we're now talking about a distributed computation as opposed to a local computation. So how do we orchestrate a group of people to efficiently talk together and so on? That's another good question. So yeah, to summarize, I think machine learning researchers, cryptographers, data scientists, engineers, I think everyone is needed in this area.
Yeah, I guess too. Thank you. So another question is, what are you planning to build in TensorFlow encrypted? That's a good question.
That's a good question. Yeah. So TensorFlow, I think if you see it from a research perspective, TensorFlow encrypted is really an attempt to try to bring two groups of people together, the machine learning researchers and the cryptographers, actually to try to form the bridge there. And then also to bring in the data scientists, as we talked about before, that should now make it easy to use these encryption techniques inside the machine learning process. The aim has also been so one thing is to kind of abstract this, integrate these two fields, abstract it so it's easy to use, and then also have very high performance. The overall goal is really to explore these use cases, to say, if you're only interested, or if your main focus is on how do you do stuff in the encrypted space in machine learning, what are the use cases of this? And we want to enable as many as possible to be able to answer that question. Yeah. That fits into a larger context as well. So in the case of OpenMined, for instance, where we're now talking about federated learning, differential privacy, and so on, TF encrypted aims to play the part of saying, as soon as encryption enters that problem, then you can use TF encrypted to do with it. But we want to kind of modularize all the complexity that's involved in these secure computations. So that means finding the best protocols for doing some kind of encrypted computation, we can put that inside one box so that the rest of the frameworks don't necessarily have to deal with it.
Okay. Yeah, great. Great to hear that. So another question is, how do you see private AI being impacted when quantum computers are here? Will the techniques used to encrypt models / data, homomorphic encryption, live through quantum computing?
A good question. So it's there are definitely some implications. They're not much different than the implications we see for basically the rest of crypto, meaning that as soon as we've solved the issues that arise around encrypting for HTTPS, for going on a website in a secure fashion, if we can solve that, then secure computation, at least for some of the techniques, are going to be solved as well. I think the only technology that can have that may need to be adapted a bit is probably homomorphic encryption, because these things are, even if some of them are based on the same techniques as those that are believed to be quantum resistant, the way they're used is not always guaranteeing for them to be quantum resistant either. So homomorphic encryption may have an impact. However, if we're talking about secret sharing, Gabel circuits, secure enclaves, and so on, there'll be little impact on these things from the quantum perspective. It's not something I'm worried about. I think there's going to be solutions. People are already working on this, and we're still years away from actually having quantum computers that pose any real threat to these systems.
Yeah, exactly. I suppose. So, is privacy preserving AI useful outside of healthcare? Another question.
Outside of healthcare?
Yeah.
So there's been a lot of applications in finance.
Yeah.
Where people have said, well, we have this data set and we can't really, we're not interested in telling anything about it at all to other people. And how can we then use these techniques? So maybe it's less about training models here. There are some companies that are looking at that in finance, saying even if we want to train relatively simple models, but we need to do that on data that's owned by different parties, we can use secure computation for that. There's other applications as well. One has been these markets that we mentioned earlier as well, where you want to kind of find an optimal solution to a market, but you want to cut out the third party that's been historically used for doing this in a privacy preserving manner.
Yeah,
I think healthcare is used a lot, maybe because there's already a significant amount of research in that sector. It's also probably the one that's easiest to explain, where you're saying healthcare data, we want to be sensitive about that, or we want to treat that as very sensitive data. And then you can sell the use case easier than in some of these other applications.
Yeah.
But I have no doubt that we're going to see several more.
Yeah, I agree. So another question is, can you talk a bit about the vulnerabilities of privacy-preserving machine learning, both in terms of security, adversarial attacks, and in terms of privacy, membership, interference, etc. attacks?
So some of these techniques are not addressing any of those questions at all. So all the secure computation techniques, they're not addressing membership inference and all that sort of stuff. That's kind of out of their domain. One way to see it is that these things they will take a function that you would normally compute on plain text data, and they will turn into a function that you can now compute on encrypted data. But that's it, you get exactly the same result. So in other words, if you have an issue with the function you're computing originally on plain text data in terms of membership, inference attacks, and so on, you're also going to have that same problem, even if you ran the function on encrypted data instead. Then some of the other techniques, there has been approaches to that. Differential privacy has been, there's been some work on using that against adversarial attacks. I'm not exactly sure what the state of the art is there. I think things are still somewhat based on heuristics, as far as I'm aware, meaning that we don't have we don't have a solid guarantee where we can say, in this case, there will definitely not be an adversarial attack, for instance, on this. In fact, there was a result that came out, I think, earlier this year, where, funnily enough, a famous cryptographer was showing that for some neural networks, there will always be adversarial attacks that were a relatively small amount of noise or manipulation of the input data is guaranteed to give you a wrong prediction and so on. In terms of security assumptions, so if we're talking about secure computation and what are the security assumptions there, those things actually hard to communicate, and I think that's one of the main problems with issues we have to solve with secure computation is how do we find a good way to talk about what is actually the underlying security assumptions, who can collaborate with who, what does it mean that half of the involved parties are corrupt? Is that realistic? How does that translate to the real world? How do we protect against these civil attacks where someone is saying, for instance, maybe I'm doing secure aggregation for federated learning, but if the adversary can, and that's his system is secure, like all the encryption is working fine and so on. But the problem is that even if you're doing aggregation of 1,000 people, if the adversary can control everyone except one of these guys, then even if it was actually a secure aggregation that was performed, the initial input of that guy is still leaked because he could control, in principle, he could send in 0 as all the other values, for instance. So how do you deal with that in the real world? How do you need some kind of identity mechanism, for instance, where you can guarantee that the people involved in this process was really who they claim to be are genuine parties that are not collaborating because they live in different parts of the world and so on and so on and so on. Those questions are still there. Yeah, I mean, I think there are, it has to be solved, and in any practical system, there's a solution.
Yeah, I hope one day. So how can we can include transfer learning concept in differential privacy?
I mean, so if I understand the question, so if you can, in principle, if you're doing training with differential privacy, and then you end up with a model, and that model you can use in other contexts like you did before. So if you want to use that for transfer learning, you can do that. It's just a model that was trained in a way that made sure that the training data was differential private. To some extent, you might differential privacy might guarantee that you're not overfitting to the training data. So maybe if you are used it for transfer learning afterwards, the model you start with is less biased. Maybe that can be an argument in some cases, but otherwise, I don't think there's any problem in really mixing the two.
Yeah, I think too. So another question which was asked like today in the chat. So what do you think about challenges to develop secure ML models over multi-model datasets and for use case for reinforcement learning?
Yeah. Can you repeat it? Sorry for that.
Yeah. So what do you think about challenges to develop secure machine learning models over multi-model datasets and for use case for reinforcement learning?
Oh, there's been a bit of work on applying these techniques to reinforcement learning. The overhead is sometimes large when you want to do that, so it can be a bit tricky to find the right application and right setting, and where this is likely to give a very practical solution. One problem is that the operations that you need in reinforcement learning are sometimes some of the most expensive operations that you can do in the encrypted space. So maybe we're not thinking about it too much in everyday life, that a multiplication is more expensive than an addition, exponentiation is even more expensive than a multiplication, and so on. But this difference is there already in plain text computations, but it's at a much larger scale when we move into the encrypted space. Where addition can be essentially as fast as plain text addition, a multiplication can be significantly slower, and exponentiation can be much slower again. And that has some impacts on the practicalities of using, for instance, reinforcement learning, or applying this to reinforcement learning. So the other part of the question was around large-scale models and training those on encrypted data. there are definitely some limitations. So the memory consumptions and so on go up when we move into the encrypted space. The computations themselves are already more expensive. So if they're large as well, then that makes it even worse. There are sometimes in order to speed up things, you kind of change what computation is being done. So as to give a concrete example, instead of computing a ReLU exactly like you would in a plain text space, sometimes you're approximating it. So you're actually computing an approximation to this ReLU instead of the exact ReLU. And the problem with that is it may work for smaller networks, but you have to be extra careful that when you move into large networks, that this approximation still makes sense, that you're still, the concrete problem is that the approximation is good within a certain interval. And for small networks, you can kind of stay within this interval. But for large networks, it becomes easier and easier to actually move outside of this interval, and then everything breaks together. Your approximation is no longer anywhere near what the exact function would be. So that's one problem that you might face when you scale to these larger systems. Yeah. But again, you can do the exact functions in the encrypted space. It just becomes a bit more expensive. So I think from a theoretical perspective, there's no limitations on this, but there is some engineering involved in actually making this efficient.
Yeah, I agree. So another question is, what is like working at Ruppert Labs, and what was it like at SNIPS?
No. I mean, it's pretty good. So we're at Ruppert Labs, we're working at very amazing technologies, right? So one thing is we're putting resources into TF Encrypted as a project. So that's great to work on that.
Yeah, I guess.
We're putting resources into OpenMined, so that's great as well. I don't think it's been formally or publicly announced yet, but we do have some announcements coming up on this. But in general, working on these private techniques, trying to figure out, is it secure computation? Is it remote execution? Is it federated learning? Is it secure enclaves? What is actually, what is fitting with the market right now? If you go out to your average guy on the street and you ask him, don't you want to have homomorphic encryption everywhere? He's going to say, yes, of course, I want to have homomorphic encryption. But then when it comes time to pay the bill, so to speak, and you say, okay, but if we do this using homomorphic encryption, then this is the overhead, this is the extra cost, and so on. Then he will quickly start to say, well, okay, maybe I'm just going to do this in plain text space afterwards. So to find that one guy, right, that one company that says, or a small handful of companies that say, yeah, this is definitely worth it for us, but we need it in this particular form to solve the particular problem. That's what we get to work on, and that's amazing, right? Because I think that's one of the big questions that we have now, that you also talked about before. Besides healthcare, actually the use cases of this, where do people care enough to actually invest in this? And that's exactly what we're exploring and what we're working on. So that's pretty exciting. Yeah. As for SNIPS, I haven't been there for a while. I think I've been going almost 3 years now. So the company might have changed a bit since. I know that definitely working on slightly different techniques than when I was there. But back then it was amazing as well. So it was a company that said from the day one, said, okay, we want to be private by design. We want to focus on privacy. Everything we have to do needs to have a sense of privacy for it. It's the right thing to do, and we believe it has a market advantage as well. So that was amazing. There was no energy spent arguing why we should look at these privacy solutions. There was a lot of interest in saying, when we started talking about these secure computation techniques, saying, well, these could solve some of the problems we have. That was quickly accepted as well. And we got to, again, play around to say, okay, there's all these different things you can do with secure computation, but which one actually fits with the use cases that we have that we believe is valuable to what we're creating right now.
Yeah, great. That's great. Cool. So another question, and what is your vision for how this stuff is going to be adopted? Who is going to adopt privacy tech first, and why?
So I think for a while, my thoughts have been that the research community is maybe the easiest one to convince. So there's definitely those that already work on privacy preserving machine learning. You don't really need to argue with them about why this is interesting, because they already crossed that bridge. What I think is missing in that space is an easy to use tool, because again, you're coming from these different fields. So you can't expect everyone to have a solid background in all of them. So kind of taking that burden away of saying you need to understand machine learning at a deep level, you need to understand crypto at a deep level, you need to understand distributed systems at a deep level. Taking some of that away was kind of the first goal to get these people on board. I think today we're seeing companies as well which are blocked by internal processes where they're saying, for instance, there was one line of work which was around using data internally in the organization, but using differential privacy to kind of block the leakage that was happening between the organizations, because the company couldn't run the risk of having this data leaked if it was all over the organization. Another one is where you have one group of people inside the organization, they have to kind of help in and tap other groups of people. But again, they're a bit blocked because they don't want this data to leak outside of the group as a way of kind of conserving the privacy and then minimizing the risk of having this data. So these guys, they want techniques for doing that as well. So I think to generalize, either people which are now, or companies which are now paying a high price for having this done using more classical means of regulation, of mediators and so on, or people which are simply interested in the space. There could be, I remember talking to one company, for instance, where they were dying to apply the machine learning and the data science knowledge they had to healthcare data in order to provide a service around this. But there was no way they could get access to this data. They ran around, they talked to insurance companies, they talked to governments and so on and so on, but none of them would give them the data. So they now have to make a long detour of trying to build up this data set themselves. Right? So they're kind of creating another company that would help them to build this data set so that in time they can use that data set to do what they originally wanted to do. So if these techniques could fit with their use case, then they could sidestep this entire process and they jump straight to what they want to do. And I think those guys are interesting as well. So people that are basically blocked, that don't have the data that they can get, but actually want to use this data for building useful services. I could see them being interested as well.
Yeah, great, cool. So there is a question is, someone who is like saying, I'm thinking of composing federated learning techniques with blockchain. Do you know if this is possible? If so, can you suggest me any project that do so?
There's been a few. I'm not keeping track exactly of who's doing it now. I think something that I'm keeping a bit closer track of is the need to have some kind of audit log for this. So the blockchain would provide that mechanism in the sense that we're doing federated learning and we can now store who did what in the blockchain and so on. But I think you don't necessarily need a blockchain for that to be useful. Just having an audit trace of whoever did what on the data, whoever computed a model gradient and so on the data. Could be interesting as well. And I know some of the systems out there, Substra, for instance, is an open source platform for doing this. That spend a lot of energy into having this kind of clear audit log of who did what on the data as progress, because there's simply a regulation requirements for their use cases. In that case, it's about training models between, I think in this case it was hospitals. And for them to do this, they wanted to have a kind of very strong audit log. It's also something that we're adding to OpenMined, both on the PyTorch side and the TensorFlow side, to be able to actually have an access log about who did what at any point in time. That's not going to necessarily prevent anyone from doing the wrong thing, but at least there is a trace of it. So hopefully that can work as a deterrent. Again, I'm sure there are someone doing it using blockchains. That seems like an obvious application. But all I'm saying is that you don't even actually need to have a full blockchain for this to be useful.
Yeah, exactly. Thank you. Okay, so another question is, how far is privacy-preserved deep learning away from production in medical image analysis, given the complexities involved in expert labeling the data?
In labeling of the data.
Yeah, in expert labeling the data. So I think it's like, yeah, how far is like the deep learning or privacy preserving deep learning away from production in image, like medical image analysis, given like the complexity involved in experts labeling the data?
So something we looked a bit at, and we do have some concrete numbers on the runtime overhead of actually doing this. Again, it depends a bit on the size of these medical images as well, because some of them are massive, and in that case, it's probably unrealistic to do it in encrypted space right now. Some of them might be more feasible. Again, it depends a bit on the use case as well. Is it worth the extra cost? Since for analysis, you don't necessarily need it in real time. So it's okay if I take a photo today and I get the result tomorrow, so it can run overnight. Maybe that's okay. So it's definitely coming. People have been looking at this for some time now. And I wouldn't, given that there's supposedly a shortage coming on doctors and so on in the near future, I wouldn't be surprised if we start to see serious applications of this within, well, let's say the next 5 years. So I know there's been some advances as well on the on homomorphic encryption to look at these type of images, I could see the cost being justified there. So let's say within the next 5 years, we probably have some serious use cases for this.
Yeah, great, thank you. So this is the one before the last question. So is it possible to get a job in privacy preserving AI yet? Do I need to get to go to grad school first?
No, I don't think you do. So it depends a bit on what you want to focus on. If you want to focus on the machine learning aspects of this, again, then I think there is, I mean, we already have some from some of my colleagues that have not gone to grad school and doing amazing contributions. So that's already a proof that you don't necessarily need to do this. And I think especially if you come from a machine learning background, it's easier to get into to what's actually some of the techniques being used here. If you want to go down the cryptographic path, so if you're interested in secure computation, then unfortunately that's still a bit harder to get into. And I would probably recommend, considering grad school for having essentially the time to study this, because there is a lot of terminology, there is a lot of techniques, there is a lot of mathematics that needs to be covered in order to really understand these, at least in order to do research. So yeah. Depend on the area. I do think if someone wants to get started, right, then there's a lot of easiest to get started on an OpenMined and TF encrypted, and you can kind of become part of the process. Again, there is 4 groups of people involved in this, and everyone is equally useful. So you don't need to be an expert in all 4 to start contributing and to start getting into the space and find the kind of the area that you're particularly interested in.
I do agree. So the last question is, have you considered using existing decentralized privacy-preserving computation projects like Enigma to provide a more robust infrastructure for AI?
It's definitely something that's been in the talks. I think in terms of OpenMined, the purpose was to create something that's larger than what you necessarily have with Enigma. So Enigma, as far as I understand, is still focused very much on the secure computation aspects of this, whereas OpenMined is this broader platform, right, where you want to have federated learning, differential privacy, multi-execution, secure computation. So it's not. It could maybe play a subcomponent. I think that was even discussed at some point, but so far it hasn't been the right solution yet. In terms of TF encrypted, the goal from the beginning there was really to say, how do we make this super fast and super tightly integrated with TensorFlow? And that also ruled out a bit, made it less interesting to look at these frameworks for building these computations.
I totally agree.
I mean, it could be done, right? And especially if you're looking at applications where you're using secure enclaves, for instance, this may make sense. But if we're talking about a distributed computation between, let's say, 500 parties using some of these fully distributed networks, running a deep neural network is going to be super slow because of the communication overhead. If we're talking about most of them being being local computations using maybe enclaves, then maybe it's fine. Maybe that's possible to do in this framework. I'm not too familiar with it to say. But yeah, I think at this point it's not clear that there would be a better solution. Yeah. At least for the use cases we've been looking at.
Yeah, for now, hopefully. So thank you very much, Morten, for your time and for answering all these amazing questions. And looking forward to see you on the OpenMined Slack channel and everyone else. Thank you very much.
Thank you for having me, and thank you for the questions, everyone. This is great.
Thank you. Thank you. Bye.